All right, getting into another video about diodes. So we're going to look at a few diode circuits here. And for this first example, we're going to say that the voltage over the diode is approximately 0.7 volts if it's conducting. Now, if we look at this circuit here, you can see that you have two diodes, D1 and D2. And the question is, how do we even analyze what's going on? Well, we need to realize that D1 or D2 can be conducting or non-conducting because it's a semiconductor. So we can say they're either on or off. But how do we know which one's on and which one's off? Well, we have to set up a table. So pulling a parallel from the logic course, we're going to set up a Boolean-like table here where we have four combinations or states for the circuit. So we can start with the first case. We can say what happens if D1 and D2 are off or non-conducting? Well, they're completely disconnected from the circuit and they act as an open. So what happens is our circuit now looks like this. And how does this circuit really work? Well, it's okay if you have a 5 milliamp source, but let's make a KCL at this point here. So if we say that 5 milliamps goes in, well, what comes out? And if you notice here, because D1 and D2 are non-conducting, there's no connection point for current to flow out of, which means this 5 milliamp source can't really be flowing into anything, which means it's not really making sense if it's even on. So does this make physical sense? No, not really. Well, let's look at case 2. And if we ignore the typo correction, what we can do, well, if we disconnect D1, we see that we would have an open right here. So we just have one loop. That's all we have to deal with. So we can start a KVL from ground and then just work our way clockwise. So if we do that, we're going to assume that we have a voltage drop over the 5 milliamp source. We're going to have a 5 volt drop over this 1K resistor. We go up 10 volts once we hit the source, and then we have a 0.7 volt drop over this diode. So we set that equals to 0, and what we get is that the 5 milliamp source would be equal to 4.3 volts. So we could say that this point Vx is equal to minus 4.3 volts. Now notice we flip here because we're going to flip orientation. Now why do we need to consider this point Vx? Well, if that diode was still here, so we can draw it in there, we would see that we are not forward biased. We don't have a positive voltage from anode to cathode. It is reversed, so it would be reverse biased, so it wouldn't be conducting. So this might be a safe assumption. But let's look at case 3. So let's say D1 is on, D2 is off, so we disconnect, or say we have an open circuit for D2 since it's not going to be conducting. And now this is our KVL loop. So we know we have, again, that 5 milliamp source. We have a 2K resistor right here, so we'd have a 10 volt drop right here, and then a 0.7 volt drop right here. This all makes sense. So we could say that this point Vx, that would be equal to 10.7 volts. But let's consider what's going on with D2, since we said it wasn't conducting. Well, if this point right here is 10.7 volts, so if we looked at the voltage drop over here, which would be the voltage drop of diode 2, that would definitely be forward biased. And if it was forward biased, we'd say it's conducting, which violates our assumption up here. So we know that this is not the case. We can scroll back up, and for our third case, doesn't make sense. Now let's look at our last case. Let's say both of the diodes are on, both are conducting. Now we're going to set up a KCL at, again, our point Vx. So we're going to say 5 milliamps goes into it because we have a tie to ground right here. We know that the point, if we are conducting just above the diode, the anode will be 0.7 volts. So we can say that this current is Vx minus 0.7 divided by that 2K. And then we can do something similar here where we just have the current as Vx plus 10 volts because of the polarity right here, minus that 0.7 voltage drop of the diode, and that's going to be divided by that 1K resistor. Now from this, what do we get? Well, pretty basic algebra to solve. We get that Vx is equal to minus 2.63 volts. Again, we run into a similar situation where if you look at Vx, if this value is negative, and we have ground right here, well, we know D1 is going to be reverse biased then, and no current is going to flow through it. So that violates our term that D1 is on. So what we can say is that this fourth case is also not possible. So if we look at all of our cases, there's only one that really makes sense, and that's case 2. And if you simulate this, what happens is we can look at our voltage point here. It looks pretty familiar. We can look at D1 and we can look at D2. Now in this configuration, D1 is in green, right? So there's no current going through it, so it's not conducting. But there is current going through D2, so it is conducting. So D1 is off, D2 is on. Now we can also look at an AC circuit here where we are simply going to take Vs as some source voltage, call it some AC voltage. We just have a resistor and a diode, and we're going to look at the output voltage. Now, in black here, we have the source voltage as a function of time, and in the blue here, we're going to have the output voltage. So if the source voltage is less than 0.7 volts, the diode is not going to be forward biased. We're going to get into that reverse bias region. The current's not really going to flow through it. And if that source goes negative, we're going to completely block that current, and there's going to be no option for current to even flow through the circuit. So we can kind of open this up, and if we probe this output, it's going to be loosely tied to ground through this resistor right here. So it'll be approximately 0. Now if the source voltage is greater than 0.7, we know that we will be conducting and we'll have a 0.7 voltage drop over the diode right here. So the output voltage would reflect that on the positive cycle. Now if we only care about the positive side of a voltage source or the positive swing, that's great, but there's a lot of time in here where nothing's going on or that output voltage is loosely tied to ground. Maybe you don't want that. So what we're going to do is add a capacitor to the output as well. Now this is where things get a little bit tricky. So we're going to recall that the displacement current for the capacitor was equal to C times dV dt. So if we have our source voltage as some input voltage VI times sine omega t, the current through this resistor right here is pretty easy, and the displacement current for the capacitor is given as follows. But in this AC cycle, there are separate conditions. We have the diode being conducting or on, or non-conducting and off. Now if the diode is conducting, what's going to originally happen? Well, the capacitor C, that's going to try to charge up to match our source voltage minus that diode drop. And after our source voltage gets to some peak, the capacitor will be charged up to that input voltage amplitude, but it will want to try to discharge through R. Why is that? Well, because this AC voltage is going to be cycling through. So it's going to be decreasing and increasing and decreasing and increasing. So approximately, after that source voltage gets to some peak value, no current will want to flow through D1. And this just kind of relates to our capacitor charging that we've looked at many a times. And after that, what our circuit looks like is this following RC circuit. We're going to say that that's equal to the magnitude of that input voltage. And what happens is that from our original circuit here in the blue, by adding the capacitor, we get the output here in the red, where you get this exponential decay. Now if we look at a circuit here in the blue, we simply have the input voltage, which is just a 5 volt AC signal. In the red here, you can see the current through the diode. So initially it wants to go through, but after the capacitor charges up, it kind of per se blocks the current. And then in the green, we have the output voltage, or the voltage over the capacitor, or the resistor in this case. So you can see this exponential decay. It's not too exponentially looking based off the values that we had, but we have this charging and discharging that occurs. Now as a rule of thumb for design, what we can say is that ideally we can spec in a capacitor based off of the average load current, the time period of the input voltage signal, and the peak-to-peak voltage ripple that we'd expect. So if you only wanted something like 100 millivolts for a ripple signal, that's where you would define that in there. But then you would also need, again, the time period of your input signal and your load current that you're going to expect. So this is where we start to get into something called rectifiers, and this was a very introductory example on something called a half-wave rectifier. In the next video, we're going to look at rectifiers. There's a few different kinds that you can have, and then we're also going to look at voltage clamping circuits. If you learned something useful in this video, like, comment, share, subscribe. Helps out. We'll see you in the next video.